样会比较清楚一点。好，谢谢。我的那个 slide 呢？好，谢谢。Hello, good afternoon. So I hope you enjoy your holiday. So we continue to chapter 3. Before further, you end of the yeah, you are going to write up some file, some file in today's okay. So in previous recall your memory, okay. Previously we have our low-pass filter, so it's Box filter and the Gaussian kernel filter, okay. So Box filter is just uniform intensity level, okay, and it depends on your mask size, maybe 3 by 3. So you have to divide it by if it's 3 by 3, so you have to 3 by 3, so you have to divide these factors to do some normalization. Divide 5 by 5, you have to divide it by 25 for sure. So the other frequently used low-pass filter is a Gaussian filter. And Gaussian filter, you have to know the equation of Gaussian. So it should be like this way. So it's G, we call it Gaussian filter. It's some constant times some exponential function. S squared. Okay, ST is the parameter in the horizontal, vertical direction. And there are two parameters you have to set. Yeah, in your homework, you have to write down this equation in your program. And K is the size of this attitude of Gaussian. Sigma will be the variance. And you will know the Gaussian shape like this one, right? So it's a sigma here. So for the 1 sigma width will occupy, I think, 68 something percentage of this the weight of the Gaussian. And you see some of this distance will disappear. So usually we design your Gaussian should have a 6 sigma. So the width of this filter should be contain 6 sigma, the width of your Gaussian. So this parameter you have to set up before use this Gaussian filter. If your Gaussian sigma is 1, so maybe you have to at least 6 by 6, but we hope it's an odd number. So 7 by 7 will be a good one. Okay, 7 by 7 will be a good one. So it is the effect we will see later compared with the Box filter. So you want to have some good Gaussian effect. The width should be considered. So usually we have the 6 sigma by 6 sigma in the horizontal, vertical direction as our design mix. Okay, so if your sigma is 1, so the size will be 7 by 7 will be a good one. If you have we'll see later. Okay, so this the coefficient is just put inside here and look at the location. So it's a center, it's a location here. So if you want to use a radius in place of the x, y, st parameter, so you can write down like this one. Maybe you can write down k e 2 sigma squared r squared, because r equal to the root of this x squared plus t squared. Okay, so it's a radius of, so here is a radius of 1, so it's square of 2. So it's the r here, the radius it will be 2, and this radius will be 1. Okay, so it depends on the location of your in the mask. Okay, so this is frequently we use for this design, and we know it's all low-pass filter. Why? Because the Gaussian Fourier transform, after Fourier transform of the Gaussian function, it's also Gaussian shape. So if it is Gaussian shape, it means your band will pass only in the low frequency band. So it's also a Gaussian. It depends on the width of your Gaussian shape. So in time domain, spatial domain, you have a wide range Gaussian. In frequency domain, you have very narrow Gaussian. If in a spatial domain, you have a very narrow Gaussian shape. In frequency domain, you have a very wide. So it's reverse relationship. Small one, and it become very wider. So it's a small. You have a very wide in your band with a wide range. Okay, so you have to know the intuitively how you design your filter. Yeah, so let's see. So smoothing filter like this low. Tofu, okay, 3-dimensional tofu, the height is 1, so it's like this one. But actually, in this kind of design also has a Lopez function, okay, like this one. But as long as you design like this positive coefficient in your mask, that's fine. But you have to normalize, okay, add up all these number in your mask and then divide it. That's it become the divided the whole sum of your mask content, and you divide by the summation, and it will become 1. So that's a design principle, okay, for your Lopez filtering. So Lopez filtering will give you some Boolean effect and noise reduction function. Okay, why? We just mentioned that your mask, like the function of this okay, let me add one more. Okay, so in time domain, if we use some 2 dimension, not instead of 3, when we see this one, this is maybe from time domain to this one, and we call it here, and the frequency performance will be like this a sync function. Okay, it's a sync function. How you do it? Please check your previous signal processing. So your Fourier transform, just like this one, minus infinity to infinity, tau t, because the time signal here is tau, and e minus j omega t dt. So transfer this to this function of p omega. Omega will like this one definition. So after you do this calculation, you will find out the result will be like this one, sine sine x here, or because sometimes parentheses. Okay, so sine x x is what's the result will be, and you know that's a joke. X here okay, about that one is it's a sinusoid, but x is increased. The result be like. And how about the origin? How about the origin? Origin is 0 by 0, sine 0 is 0, right? X 0 is 0. So 0 by 0, you have to use the Haskell rule, the derivative in a denominator and a numerator simultaneously. So it will become when x equal to 0 here. And so what's the result? So it becomes cosine x and 1. S equal to 0, so it becomes 1. So this is will be 1 in the frequency domain. Okay, so you'll see the same function in your frequency domain. And if you take the amplitude of this filter for this box filter, we call it rectangle pulse. Okay, so magnitude. So you will look at this. It will be centralized in the low frequency band. So actually, the box filter here in spatial domain. So there's some ring effect there. So this is not very easy design in your spatial domain, but the green. So the result like this. Okay, so if you do some mathematical derivation, and you will see the box filter in your green domain is like a sinc function over there. We define this one as sinc. Why you say sinc? A sinc of omega. So it's a sinc function. Okay. So it's in your time domain, you design is very easy one, but in green domain it's a low pass filter indeed. Okay. Everything you can do some Fourier transform and look at the frequency band power spectrum. And for the Gaussian, so we just mentioned Gaussian after your Fourier transform in green also Gaussian. It changes in the bandwidth. Okay. This is the low pass filter design here. Let's look at some example. So this is the box filter design. Okay, and depend on your mesh size. It's n by n here. So that's divided by n squared, and this original image. So it depends on your size. So when you have a large just use low pass filter, you will remove high frequency band noise. So you increase your SNR, signal noise ratio. So that's the way how you remove the noise. So here, but you have sacrificed some image quality. So use low pass filter. You can see when your size bigger and bigger, you just remove more your noise, but you sacrifice your original power spectrum. So your image will become blurred. Unfortunately, become blurred. So it's depends on how you solve this. Your image you can look at. So how many active noise in your original image? You perform this low pass filter, but unfortunately, if your mesh size is big, you will get this result. Okay, but for the image enhancement, we say there's no special way to see it's good or bad. For example, if you put my image here, maybe it become better effect, right? So become smaller, it become more handsome. If you too clear of my image is bad, it's ugly. Okay, maybe some pimple, some dots there, and you use this low pass filter, it looks better. So I say there's no specific criterion for image enhancement. Sometimes blur image will be good, especially for a human portfolio. Okay, the face. Okay, so this is another example here, and we added some. This is noise free. This is noise free image. Okay, and this is the zero mean Gaussian noise with some variance. So we add some Gaussian noise in this image, so you can see there's some noise here. It's original image, camera man, and use some additive noise, and then use some. This is use like this box filter. You can see the noise is removed, all right? But also the quality of your image becomes blurred. So it depends on how you do. If you want to evaluate is that good or bad, we just mentioned we can use SNR, signal noise ratio, right? So it's like use power spectrum of your removed image of your signal image PS divided by P noise. Okay, take log If this power, the phase will be 10. Okay. So it's power of your signal. So you have to calculate all the power of your signal divided by the noise, and you will see what's the signal noise ratio. So you have to see which one is higher. Higher is better for sure, because signal divided by noise. So if your image contain more signal energy, so the number of the SNR should be higher. If you just only have the amplitude, you are not going to calculate this power spectrum. So you can use amplitude of your signal, amplitude of your noise, or also can signal noise ratio for image. So let's look. This one is additive noise with Gaussian additive noise. The variance is 0.01, and this is the Gaussian additive noise with a variance. Variance is the width of the Gaussian. You see, when this is larger, 0.05. So it's the degraded image is more even worse. So you can see these two images. So the variance bigger, you add more noise for this image. So it's getting worse. But you use the same this box filter. The result, you can remove those more major degraded Gaussian, and this look like okay. So but the image again is blurred. Okay, blurred. However, the signal SNR is increasing after you do this filter performance. This is the example we mentioned in previous slide. Saying if you have okay, so remember this is the spatial domain, time domain to frequency domain, and it's a sync function, right? Amplitude of we can take the. However, because the energy, which the Fourier transform of the sync function is box. Okay, so it's a duality of the Fourier transform principle. So here it just give you, if you want to design an ideal low-pass filter, what's the ideal? And I have a very vertical cut here. So the frequency up to U0, I will maintain all the pass band here. And larger than U0 is harder. So it's ideal. It's designed in your frequency domain, right? It looks like easier, right? In frequency domain, I use an ideal low-pass filter, and there's a clear cut-off frequency here. Okay, so all the energy, all the signal larger than this one was discarded at this point, U0. If you design here, like this one, I'm going to design an optimal low-pass filter. What's the time domain? So it's inverse transform. So it's your design frequency omega here. So what's the inverse in time domain will become look like this one, because we know the Fourier transform is a duality. There's duality. It's very easy to prove. You just change the parameter. You will see it's later the same idea here. So duality of the Fourier transform, you will see in time domain you have to design like a sync function there in your time domain, and you get an ideal low-pass filter. That's possible. So unfortunately, in your real application, you cannot design an infinity. So go to minus infinity, positive infinity in your spatial domain of the mask. And then the size is like a sync function, but go to infinity to apply on your image. You will get an ideal low-pass filter effect. Okay, so unfortunately, it cannot be satisfied. So in time domain, spatial domain, maybe we will have a limited. So in our frequency domain, you cannot get the ideal one. So see, if you do this in time domain, very easy box filter, 3 by 3, 5 by 5, 7 by 7. But in your frequency function, it's a low-pass function, no doubt. But unfortunately, the effect is not ideal like this low-pass filter, ideal low-pass filter. So let's see more example here. This is the test pattern of the size 12, 10, 12 1024 by 1024 pixel. So the image here, yeah, and B to D result low-pass filter and use box kernel. So use 3 by 3, 11 by 11, 21st by 21st. So just ask you to remember what's the result look like. Okay, so when your mesh size is larger, and the result getting blurred. This is the result, but there's no additive noise, so you cannot compare. And this is the distance from the center of various size of square kernel. So it's the distance R here we just mentioned. So if you use your Gaussian filter, you have to know what's the distance according to the original location. We just mentioned that one. This is for k equal to 1, sigma equal to 1, 3 by 3, that's this one. So you just calculate by this exponential minus exponential minus 2 sigma square r square here. So it's k, so if you k equal to 1 and sigma equal to 1, and your location here is root r equal to root 2. To add up all these coefficients and then put a summation as your previous parameter. Okay, and this one will make the summation and their deduction dividing by this coefficient will equal to 1. So the add up will be 4.8 something. Okay, so this is a very important. Otherwise, your pixel will be a higher energy. You added higher energy there. And here is some, just give you some idea. What's the relationship between the multiplication and convolution? We just mentioned convolution is different from multiplication. Okay, so every filter design in your system, it should be convolution. It's not a multiplication directly, one by one. So you perform some multiplication. If you have two Gaussian function and then put together, depending on your operation there. If your multiplication there, you have a new mean of this one. But if your system is a one by one cascade together, and they have a correlation, a convolution relationship, the mean is become first the Gaussian wave mean plus the second Gaussian filter. So, and for the sigma, for the variance, the standard deviation, you will become like this one, and this one become like more complicated if your operation is multiplication. But however, this is putting the problem. If you are interested in the mathematics, please go ahead to derive by yourself. Okay. So here, let's see. There is a test pattern of this image. Okay, we just mentioned. We try to compare the Gaussian and the box filter. Okay, we mentioned the size are different. The box filter is very clearly 3 by 3, 5 by 5. How about what's the relationship between box filter and the Gaussian filter? What's the size? They are different. You here for the test pattern on the result low-pass filtering for this by 21 with standard deviation sigma 3.5. So now you know why it's a 21 by 21 size. Remember, we have to multiply 6, right? 6 sigma. Okay, so if you multiply, your sigma is defined as a 3.5 for your Gaussian width. And your the variance standard deviation is 3.5. So it hence this one. So it's a result is 21. So it's odd number, so it's good. 21 by 21. So if your sigma set to 7 for your Gaussian, so you need 42 by 42, but we want is odd number. So maybe 43 by 43 is good for that. So design this one. So you see, this depends on your sigma definition, your standard deviation. You are going to define different mesh size for your Gaussian. And what's the result? We say if you have a higher sigma, higher factor, is that 6 times sigma? Is that affect your result? So let's see. We mentioned 6 times is good enough because 6 times This sigma is occupied maybe 68, 69%, and 6 sigma. Okay, I'm drawing not good. So 6 sigma may be good enough. If you have a higher mask size, will that affect your result or not? So let's see. This is an example to demonstrate. It doesn't matter. If you keep increasing your mask size, you just waste your time for the computation. Okay, so here's the example for this filtering using the Gaussian kernel 43 by 43. Why? Because we mentioned this is the sigma equal to 7, the Gaussian size, the weight, and we use 43 by 43. For the same image, if you apply for the 85 by 85 mask design, but you use bigger mask size, okay, and apply on the same image, and see what's the difference result. So the result is just minus these two. So what's the result? Nothing there. And they tell you what's the highest number in this mask, in this result difference image. When your gradable is 0 to 25 to 56 gradable, and the highest number in the difference image is only 0.75. What does that mean? It means it doesn't matter. If you use 6 times sigma, good enough. You don't have to use 7 times sigma, 8 times sigma size. Not necessary at all, because they are different, making no differences. Okay. Yeah. So and to compare, when you have let's see what's the result here, and for the box filter, yeah. So you have to look at this the result for your Gaussian or box filter design. We just mentioned choose the right max size. So here is the profile: white rectangle, black background, and horizontal intensity profile along with the scan line. And what's the result for using box filter and Gaussian filter? Okay, so it's image. A is the image. Okay, it's the black and white, and you take a cross profile here. Okay, cross profile, and look at the shape of the signal. And this one original is like this square, right? The white is the high intensity value here, and the black is the low intensity here, right? So the BD result is use the low pass filter with a box kernel with of the size 71 by 71. So for this image, we have a 75 by 75, 71 by 71. Oh, this one here, and then the corresponding intensity of the C is the result of smoothing filter. Use 151 by 151. Okay. So the result you can see for the box filter, the crossfire is just like this stepwise result. But for the Gaussian, the result will be smoother. Okay, when you process this one, it will be smoother, and the image rectangle size, the image of the rectangle are the size of this is a 12 of 1045, sorry, and for the rectangle, the 768 by 128. So I just tell you the Gaussian low pass filter will be smoother. Okay, the edge will be smoother compared to the box filter there. Okay, so here is the result of filtering the pattern, the same image using. Okay, so this is just remind you, you are going to use some low pass filtering on your image. Remember, we just mentioned the folder effect. You have to look at it. So our homework give you some low pass filter, high pass filter, some medium filter. So at the beginning, you have to paint your folder to make your result better look. This one is use zero padding. Zero padding is if you have you just add in zero. If you have a 3 by 3, you will add one more column, one more row, zero outside is zero padding. If you are using 5 by 5, you have to padding two load, two current simultaneously, or 5 by 5. Otherwise, your border pixel cannot be solved because your mask will be put on here, right? Okay, so how you process this border outside of the image? You have to do some pre-processing before you use the mask operating. So the first is zero padding. So what's the zero padding? Just adding zero on your border, outside border, 0, 0. But unfortunately, the result is look bad. Okay, because there's some extra additional edge occurred in your image. And the second one will be what? Mirror padding. So the second one, mirror padding is depend on your image here. For example, if we have this size, so mirror padding is like this one. Okay, so like a mirror, you reflect your inside image. How deep of your how big of your mesh you have to look how deep in your image inside. And the third one is replicate padding. So it's replicate padding also can be accepted because this one is 4, 3, and padding is easier. Replicate padding is easier. So just extend your outside intensity. Okay, so the third one is use replicate padding in the third one. So you can see the second approach and the third approach, you'll get a better result, especially on the border. Provide your homework to the grade is not good as others. Okay. So it's like the border. You can do that one. So here is the test pattern of this big size. If this is the 1496 larger size, higher resolution compared to the previous one. Okay. So this is the result. Use a test pattern of same Gaussian. Okay. See the result of filtering using the Gaussian kernel with okay, so it's also use a mirror padding used throughout. And here is try to save up 3 by 3. Okay, I think it just gives you some higher resolution. So it really depends on your input image and the mask, the relationship of your image. Some telescope image, and so for the low pass filter, sometimes we want to extract your object. Okay, it's one of the application. For example, like the optical character recognition. So you want to take the image. So sometimes your image must be degraded by some different noise. Okay, and you are going to extract the major object from your image. The first way is use low pass filter. We always use low pass filter to smooth out your image and take away some irrelevant object. So for example, like this one, and you want to find some major component from this image, and first of all, remove the noise. So this is B is use a Gaussian noise low pass filter, and then after that, the second procedure is uses segmentation. Okay, here you use some segmentation, maybe some set of sovereign of the new stock, and some filter scale to 0 0.5, 0 to 1, and you use 0 0.5 to threshold. So maybe you can set up 128 intensity level and see what's the result. And then you will extract the major object from your image. So that's some old trick. Okay, you use a low pass filter and then thresholding. You can get some major segment. So your image. So for example, like optical character recognition, you scan the image and it's become gray level intensity. However, recognition, you don't need gray level characters. you just need a binary image. So how you do that one? You just smoothing, remove the noise first, and then use thresholding, become binary object, and then detect location of the object, and then try to do more research. And use lossless filter, it works well. How about this one? If you look at this one, so, but maybe you will ask me, what's the threshold number here? I just, how you get a 0.4? I don't know the answer, really. It's based on your image. Maybe you will try 0.5, maybe better. Threshold detection. Okay, so you have to try it and see what's the better result. How about this one? But it's obviously because the image, the noise evenly distributing on your image. How about this one? If you look at this one, remember this image? Actually, we mentioned this in previous slide. We say if you have this device, easily, I can detect what kind of environmental noise. How you do it? Your real system, your device, how you detect what's the additive noise in your image. How you do it? Remember the impulse function, right? I have the camera, I have everything at hand, device at hand. So all I have to do is give you impulse function in your input. So if you have all your system, what can you do? You just give a impulse function here, delta t or delta xy. What's the delta xy? It's only point source, point lightning source as the input. Give your input. So what's the result? It's that's a convolution, right? And it's overall is like a filter. I don't know what's that. So everything delta xy combine your filter. What's the result? And you will get this system. So we use edge. Sorry, let's use edge as our system. Easier. Edge. So the edge is you want to find impulse function of the system. We call it impulse function of your device. So we call it system function actually. So how you find this? You don't know at all. The only way you try to experiment immediately is a point source. Okay, for the voice, you just have a one-click sound. Okay, go to you just have a system. You just one impulse function energy inside your system, and you measure output, right? Sorry, I scare you if you just fall asleep. Okay, so it's input. Yeah, you go to the maybe you go to the mountain for this long weekend, and you just go to the mountain and say and then you get some echo, right? You just record it. This is the system of the mountain. Okay, the filter of mountain. So you just correct it. Later, you just put this signal with your speaking voice. You just like you go there and speak in the voice and you get a response. So this one impulse function is a way to measure your system performance. And if you go there and you see, the system perform like this one, so that's good. Just record it, tap it, or save the image, and this will be your system. However, and next time, don't use one. Next time you use your input one, maybe your F1, XY, and you will see you can predict what's the result of your system. If you put any different signal image, any signal, any image, and you will get a result output through this system immediately. So do some convolution operation. However, when you get an image, you don't have a system, unfortunately. You don't have a system. So how can you do? I just only have this one. I don't know what's the device create this image, but I know there's some error inside this image. So how you do it? Okay, maybe you can try this way. Okay, so here's the image, right? And you know, there's some shaded effect. So it's non-uniform. It's non-uniform. So how can I do? The answer is low-pass filter. Okay, we just introduced low-pass filter, so you can guess immediately. Low-pass filter, right? Okay, so try to use low-pass filter. We say it's a shading illumination. So we try to correct this shading effect. So use low-pass filter. So here, use small. So depend on your image size. So where is this image size here? I didn't have this one. This Okay, so I think I don't know if I write this right. So this most is 128 by 128. Oh, okay. I saw. Okay, this image is 2048 by 2048, and this small square is 128 by 128. So sometimes we can use about 6%. So it's a suggestion. Around 6% of your image size. Try to see what's the result. Actually, we don't care about the content of this image. Okay, we just use 60% of this size to grade it, to low-pass filter your input image. And then after that, see, that's the result. Okay, 60%. So what's the, it's what, 2048 times 6. So it's about 128 already. Okay, so, and it's small size, and let's suggest, because you are going to, this is the one time, so 4 times larger for this small object, because we are going to smooth out everything. We are going to blur everything in your content, make it like this one. So how do you do? Use this one times about 4 times of this mesh size. So you have to use this one by this one, 128 by 4. So very big mesh size. And then after you apply this low-pass filter, it will become like this way. Smooth out. And then smear all the image like this one. So what's the result? So can you see the shaded illumination there? Shading effect. Okay, shading illumination for this image. But for this one, some darker. Don't care the photo, because of the major out all the image, and then divided this one by this one. So if this is A image, this is B image. So A divided by B will be C here. So take a comparison. It's also another way to solve this problem. If we don't have a device at hand, we cannot put an impulse function in the device. No way. And what can I do? I just try to find out what's the shaded effect of this image. And how you do that? Low-pass filtering. But now you are not going to remove the Gaussian noise, remove the additive noise. I'm going to smooth everything out. So I need to use a bigger image mask. Okay, low-pass filtering mask, larger one, to smooth out everything there. And then divided by this one. So the result of A divided by B, get this result. Okay, so when you perform like this one dividing operator, make sure divide by 0 will be protected in your M file. Okay. So that's another trick for low-pass filtering. A lot of application you can use this one. So low-pass filter always is a rugged and approach to make your image smooth. So as I just mentioned, the smooth may be good, may be bad. It depends on your application. For this one, I use larger mask to smooth out everything. And then look at the shading effect. Because from here we know it's some shading illumination here from dark to bright. So maybe the light is in different direction. How can I move it out? This is a way you can try. Okay, so up to here we have the linear filter, because the low-pass filter is the linear filter. we can remove the noise. Active noise, Gaussian noise. Use low-pass filter immediately, very easy. And now we are going to introduce another nonlinear filter. Nonlinear of the mask. Okay, the linear filter is just add up the 3 by 3, add up all the 9 coefficients together, divided by the coefficient. Okay, for example, box filter divided by 9. It's a linear operation there. Multiplication and summation. But now we are going to introduce nonlinear. It's also very important for some degrading noise. It depends on your noise type. Okay, so sometimes in your image, you get a good result because you share out the error to your its neighboring pixels. So it's not good like this salt and pepper noise. Okay, it's not good for use linear filter. So now we are going to introduce nonlinear filter. So it's very easy. Okay, because previous we say a lot of noise is distributed by this Gaussian pop, but it doesn't work for the spike noise. So because averaging you will blur out your neighboring pixels. So when you have a spike noise 0 or 255 occur in your image, you will smooth out, share out the noise to your neighboring. But if you use order statistics, okay, order statistics, which means in this small mask, you are going to sorting, ordering all the pixels occur in this neighborhood, and then replaced by some your rule, and it will help you to remove the spike noise immediately. Okay, so for example, the median is like this design. So it's the result of this mask will take the if you have a k pixel in your mask. For example, like this is 9, 3 by 3 mask is a 9 pixel, and you are going to sorting all the pixel value in your image located in this area in your neighboring, just sorting it, and then the output of this filter will get this one. If your k is even or your k is out, is easy. It's just k plus 1, 9 plus 1 divided by 2 is become 5. So the fifth element will be your output. And if you use your mask is even number, so it's only k by 2. Okay, take a k by 2 like this, 2 by 2. Okay, so the k equal to 4. So the second one will be your output value. So it's just counting how your neighboring, and then sorting your image, sub-image, and then get the median value as your output. So in that sense, you can imagine if there's an image there, okay, and there's a spot, black spot is 0. So it's a neighboring for this black spot will be replaced by its median number in this small mask. So the black spot will disappear immediately, right? So the spike noise, we call it the salt and pepper noise, never use linear filter to solve it, because you will share out, the linear filter will share out the noise. But for the nonlinear, it's an order statistic filter. You just calculate, sorting the mask neighboring pixel, depend on the size, and then sorting, take the median value, replace the output as the output, and it immediately will get a very good result. Okay, so we'll see it in next time. We still have a lot to compare. Okay, so we have maxima filter, minima filter, median filter, and chapter 10, I think, chapter 9, morphological filter, all nonlinear filter. We'll introduce it later. Okay. So to already put on the website, right? Okay, there are 2 problems to calculate. Make sure you can do that, because you'll see it maybe 2 times. Quiz on November 1st, right? Or October 30. October 30, our quiz one. Midterm will be November 11 something. I was in Germany. So make sure you know how to do it. And 3 M file to create. Low pass filter, high pass filter, medium filter, and high pass filter, I think. Okay, so follow my direction to design your M file. Okay, if you have questions, come here. Otherwise, press dismiss. Or 那这个还有我一个玻璃展一下，我是不是只有这些东西？
老师，这个线是我，
这线是你的嘞？
老师那个回去的时候可能要充电，因为我今天拿的时候它完全没电。
哦，是哦。
开机，对。
所以充电要，这是都你的？
对，都我的。
啊，我就这样子。
对对对。
好，那我马上回去充电。好，OK，谢谢。
这个